thank you for the introduction. Thank you for inviting me to speak here. Yes, I'm James Wootton, and I am indeed from IBM Research in Zurich, but we're also going to have Amin talking, who has been working with us here in Oxford. So I'm going to be talking about procedural generation, and I'm going to be talking about I'll be talking about one application about that, and Amin will be talking about another, which is quantum natural language generation. So to start, what is procedural generation? It is a huge space of applications where you generate content using an algorithm. So what is content and what is an algorithm? Well, both of them can be pretty much anything, so that's why it's very broad. But for example, you might have in computer games, you might want to generate levels, you might want to generate maps, you might want to generate the text spoken to you by an NPC, and you're generating these things according to certain constraints, like your level has to be completable, puzzles have to be solvable, the NPC should make at least some degree of sense. So there's a lot of different computational problems that you can define in here. So people have looked at quantum music generation. As we've just heard, that could also be regarded as a type of quantum procedural generation. So in procedural generation, there's many kinds of methods that can be used, and I like to think of it as an easy corner and a hard corner. In the easy corner, the generative thing is just creating some nice patterny thing that you use to make into whatever it is you're making. So just some nice natural looking texture can be used to texture a surface in CGI, or it can be used to make a map that you could use in a game like Civilization. And these are quite easy to generate. But on the other side, well, the thing you're generating is going to have certain constraints that you want to meet. If you want to put those all in your actual generative part, you're going to have to be solving constraint satisfaction problems, or at least approximating solutions to constraint satisfiability problems, which are really hard. So that's a very computationally hard end of procedural generation that people currently try and find ways around. With a quantum computer, we could probably just go straight through. So I think this field offers a unique opportunity for quantum computing, because already with current computational resources, we can do useful things in the easy end, and we can see with things like constraint satisfiability problems how we'll be able to do things in the hard end. And so as the technology progresses, we will get ever further along this route, and we'll get ever more sophisticated. So in this talk, we'll be looking at two works. One is on our first step, or I like to call it the 0th step into quantum procedural generation. That's the one I'll talk about. And the other one is quantum natural language generation, which is what Amin's going to talk about. So let's get on with my bit. Our step 0 is something we call quantum blur, and I'll just give you a small introduction to it for the context of the next few slides, and then talk a bit more about it later. So this is an image manipulation effect. You take an image, you encode it as a quantum state, and then you can turn that quantum state back into an image. If you just do that, then you get the same image, which is kind of boring. But if you stick down a quantum circuit in between, then those quantum gates will manipulate your image in some way. And so this was made to be designed for small numbers of qubits, easily and even more easily done on a simulator than on real devices. And the intended uses were to give people something to do in a hackathon project if they come to a hackathon or a quantum game jam without any real knowledge of what quantum computing is beforehand, or to serve as something that people can use in education, because slapping down some gates and seeing what they do to a histogram, it's not all that fun. If you've got, instead of a histogram, some images, it could be better. And also to be able to write a paper to say, we're doing quantum procedural generation. This is our first step. We're here in your procedural generation academia now. Get used to it. So we wrote such a paper. We've used it in hackathon projects. So all of those things we've done. But then we've gone on to see that people have been using it for more than that. So like I thought, once you get the paper out, that's kind of, this project is underlined. We move on to more sophisticated uses, but instead we're seeing it being used by an indie studio an indie game studio in Finland is using it for procedural encounter generation, basically using it as part of a very simple AI in a game that they are making. And this AI is the mind of the rogue AI that is the antagonist in the game. And so the fact that you get the quantum interference patterns are giving you something which is obviously a pattern. It's giving some sense of an intelligence behind this rogue AI, but it's also a bit weird as it's quantum. Also, we've seen used by artists. So there's this artist, Libby Heaney, who you can see things from her Twitter here. She used it in the KidsKitKat Europe project. So that's like the hackathon intended usage that I talked about earlier. But she's then gone on to use it in more sophisticated ways in her actual art. And also we have an artist called Roman Lipski who has used it even more extensively. So he's someone who was a classical painter who started to experiment with using AI as a muse to allow him to develop an abstract style. Now he's moved on to using quantum blur as essentially a paintbrush, which allows him to do more and interesting kinds of abstract art. And you can see some examples from his Instagram now. So he actually had an exhibition last November where he had examples of images that he had created, so pictures that he had created as a classical painter, and then modifications of those into new artworks that he had made using our quantum image manipulation technique. If you look at images from this exhibition, you'll see something sticking out like a sore thumb, which is an academic poster, because we were also there to explain what we were doing. So imagine, if you will, you're not sitting in a church in Oxford on a Monday morning, but it's Friday night, and you're at an artist studio in Berlin with a glass of champagne in your hand, and some weird scientist in front of you trying to say stuff about quantum stuff. That bit's not so easy, not so hard to imagine, I guess. And I'm going to take you through that poster now. So some of the details. So quantum blur is works on monochromatic images. So an image, what is it? It's a set of pixels, and each of those pixels has a brightness. And so you can assign, if you assign a bit string to each of those pixels, and you can turn that image into a superposition using the amplitude as the brightness. So it's an amplitude encoding of the image. But the important thing is it's done such that you don't just take the coordinates and write them down in binary to get the bit string corresponding to each coordinate, but you use a special encoding such that nearby pixels have nearby bit strings. So the Hamming distance is 1. There's only 1 bit difference between any two neighboring pixels, which means that if you go in with something like a small angle rotation, it causes amplitude to bleed into neighboring pixels, giving something that's a little bit like a blur effect, but it gives you interference effects as well. So there's multiple different things that you can do with this. You can stick down any circuit and get different kinds of effects. The one that I usually do is just do small angle RX rotation, so rotations around the x-axis. And this causes a sort of this blur-like but quantum interference effect. So how does that compare to a normal blur effect? Well, we've got these graphs here, and these quantify for an image when you apply some sort of blur effect. What is the difference to the original image as you turn up the blur? How much asymmetry is there in the image? How much detail is there in the image is two different definitions of that here. And for a normal classical blur, as you blur it, it becomes more different, which is what we are seeing there. As you blur it more, the asymmetry and the detail disappear. So basically, everything interesting about the image disappears as you blur it. This is not a groundbreaking discovery that we made. But for the quantum blurs, if you look at the blue one, which is the RX, again, as you increase the amount of the effect that you're applying, you get increasing difference from the original, but the asymmetry goes down a bit and then remains relatively stable. the detail goes down a bit and then actually resurges. So what you're seeing here is that the difference of using this kind of thing, this kind of image manipulation, is that you don't lose the interesting features of the image. They just get recombined in new and interesting ways by the quantum interference effect. So this is actually we very much need coherence for this, and the green line is what happens if we imagine a version of this where there's no coherence and we just get all of the interesting things going down to 0 at some point. So interference is required for things to remain interesting. Also, we can stick this in a matrix product simulator and artificially turn down the entanglement, and you find that for a given image, if you turn down the entanglement, so it's not very clear here, but this is an aerial photograph of a town from above with a river coming in here. And this really, once we turn down the entanglement, it just becomes horrible noise. This image of some trees and a lake has symmetries that are easier to replicate using this process without much entanglement. So it remains kind of recognizable for a long time. But nevertheless, if you want to do any image of any sort of interesting detail, you have to use entanglement for it as well. Yeah, and as I said, it was designed to kind of work on simulators. So this is step 0 on our journey. We have to now go to more sophisticated things, to things that actually need quantum computers and use them in more sophisticated ways. So another piece of work that I'm not going to talk about here is geopolitical map generation, which really does run on real devices. And of course, there is also the thing that Amin's going to talk about in a moment. But just to say what we use this for in terms of procedural generation, originally it was in map generation. We used it to generate these voxel-based maps for a Minecraft-like game engine. So I'll leave some references on the screen while I hand over the mic to Amin.
So I'm going to switch gears now a bit and talk about this quantum natural language generation work that we've been doing. And once again, this is joint work with James and also Marcel Pfaffhauser from IBM Quantum. And again, you should think of this as step 0, I guess, for quantum natural language generation. So we wanted to build upon this work that's already been done for quantum natural language processing, which I'll tell you about in a moment. And there's an outreach and educational goal to it as well. So for instance, there's all sorts of courses now that are aimed at people like high schoolers to teach them about quantum computing and quantum theory. And we think that a project like this could be something nice that you could do at the end of such a course. So before I can tell you about generating language, I need to go over some existing work that's already been done in QNLP, because our work really builds on top of this. And the first thing I want to talk about is this pipeline that's in a paper called QNLP in Practice. I think lots of the authors are here, actually. And this pipeline essentially gives us a way of going from any language, any sentence in the English language to a quantum circuit that in some way encodes the meaning of that sentence. So let's talk about that in a bit more detail. The first thing you need to do is actually extract these diagrams that we saw in the first talk today from a sentence. So let's say, and I'm sorry if you can't see this very clearly at the back, let's say that the sentence I have in mind is, person prepares tasty dinner, right? You can extract a so-called disco cat diagram, that stands for distributional, compositional, categorical diagrams. And essentially, in these diagrams, you have words being represented by boxes and wires which connect these boxes together according to the grammatical structure of your sentence. So in this case, if you look at the word prepares, this diagram is essentially saying that if you give that word a noun on the left-hand side and another noun on the right-hand side, it's going to output a sentence for you. And that's actually also how we know this diagram is grammatically well formed, because you can see there's a single output wire that has type sentence. Now, quite crucially, these diagrams, I mean, they're more than just simple pictures. They're based on the rigorous formalism of monoidal categories behind the scenes. And so that means they come equipped with a calculus that allows you to rewrite the diagrams. And this rewriting step is very useful when we're dealing with near-term quantum computers because it can save you some, it can essentially make the quantum circuit that you extract in the end be a bit more efficient. So perhaps it may use less qubits if you perform some rewriting steps. Although I guess this is strictly an optional step. And then once you have your rewritten diagram, we've already heard that quantum theory can also be formulated using similar diagrams and things that are based on the ideas of category theory and monoidal categories in particular behind the scenes. So you can extract from your diagrams a quantum circuit. And there's different ways that you can go about extracting this quantum circuit. So you may hear the term ansatz for QNLP being thrown around. And that essentially means the way in which we're going to extract the quantum circuit from the disco cat diagram. And then finally, you can use a quantum compiler to transform this circuit into something that you can run on an actual quantum computer, right? So this is the connectivity graph, I think, for IBM Q Guadalupe, which is a 16-qubit computer. And yeah, you could use a compiler like Cambridge Quantum, or I should say Quintinium's now TCAT. There are other options available as well. OK. So once we have this pipeline, what people have done is they've trained a hybrid quantum classical sentence classifier using it. So the idea here is that you start with a corpus of sentences, and each sentence in this corpus belongs to one of several possible classes. And then you create a quantum circuit for each of the sentences. I should have said these circuits are parameterized, so that means there's some values, some parameters that appear in them. Like if I go back to this slide, you can see there's these alphas and gammas and betas. Those are parameters that you can tweak around and play around with in your circuit. So once you've extracted a circuit for each sentence, you can then use classical machine learning techniques and continuously run these circuits and measure the outputs to see if they're correctly classifying your sentences. And then you change these parameters until you end up with an optimal set of parameters. And that's the hybrid part, really. So we're combining classical techniques with something that's being run on a quantum computer or a quantum simulator. And again, people have done this. None of this is our work yet, but people have done this for binary classification examples. So I think for a corpus of 130 sentences, some of which are about cooking and some of which are about IT, you can train this classifier. And these diagrams at the bottom essentially tell you that the idea works. So this is running it on a simulator, I think, and the one in the middle is running it on a real quantum computer. OK, so now we get to our work, the novel part of this. And our idea was to build on this hybrid quantum classifiers to perform a simple sentence generation task. In particular, the task that I want to solve is the following. I'm going to ask this computer algorithm to generate a sentence with one of the topics that it's been trained over. So if we think about the cooking versus IT example, I could ask it to generate a sentence about cooking, and I wanted to output for me a sentence with that topic. And to solve this task, we're essentially going to treat the task as an optimization problem. That means there's a search space of possible sentences. So in this case, it's all the sentences that you can build out of the vocabulary which your classifier is trained over. And you can see that in this search space, there's going to be all sorts of sentences, right? So they might be sentences that have the incorrect topic. We don't want to output those. There might be sentences that have the correct topic, but they're semantically nonsense. So dinner cooks man isn't a very meaningful sentence. There might also be sentences that are both semantically incorrect and have the incorrect topic, OK? And that's an optimization problem because you're searching for some optimal solution among a possible set of solutions. So once you formulate the problem in this way, there's a lot of off-the-shelf techniques that you could use to solve it. In our case, we're going to use a variant of simulated annealing to solve it. And I won't go over what simulated annealing is exactly, but I will go over an example of how it would work in this case. I will say we chose simulated annealing because in classical natural language generation, there have been some recent papers where it's been very useful for performing tasks like sentence paraphrasing, which are, again, a generation task. So before I go over the example, I just want to tell you what a neighboring sentence is, because this is something that's used in simulated annealing. The idea of a neighboring sentence is essentially that you need a way of navigating your search space. So given a sentence, I want to go to a sentence that's somehow close to it within my search space. And I can do this by performing one of three possible operations. So this is essentially a generalization of Liebenstein distances to sentences, for those of you that know what that is. If I start with the sentence, person prepares dinner, I could insert the word tasty, and then I get person prepares tasty dinner. Alternatively, I could substitute something. So I could substitute the word person with Alice, and then I get Alice prepares tasty dinner. Or I could delete something. So whenever I perform one of these three operations, I'll say I end up with a neighbor of the previous sentence. How much time do I have right now?
10 minutes.
Oh, great. Okay. So I'll just finish with a toy example. This is going to be a task for generating sports headlines. So we actually trained a new classifier that classifies news headlines. So it classifies news headlines into one of four possible topics: sports, entertainment, tech, or politics. And this toy example will guide us through how the classifier might generate a sentence about sports or a headline about sports. This isn't an actual run of the algorithm. The actual run will have many more steps involved, but this is just to give you a flavor of how it would work. So I'm going to start with some initial candidate that could be chosen heuristically or randomly. And in this case, I've started with this sentence: Johnson continues new policy. I'm going to extract a parameterized quantum circuit for that, using the techniques we've already discussed. And I'm going to run this circuit many, many times. I'm going to run it with the optimal parameters that my classifier has been trained over. And I'm simply going to count the number of times that it outputs or it classifies it as having the topic sport, right? And then if, say, more than 95% of the time it classified the sentence as being about sports, I'm going to output that sentence and say this is with high probability something that's talking about sports. So in this case, only 5% of the runs ended up with sports, so we need to generate a new sentence. And I'm going to do this by performing one of those operations that gives me a neighbor of my current sentence. So I'm going to delete the word new, and I end up with Johnson continues policy. And you can see now it thinks that this is more about sports in a sense. The probability's gone up from 5 to 7. But it's still predominantly thinking this is a sentence about politics. So I'm going to continue and generate another sentence. This time I'm going to substitute the word policy with the word winning. And actually what happened here is that the probability of it being about sports went down. So it thinks that this was a bad move, basically. And what the algorithm does in this case is going to revert the change. So we go back to our previous sentence, Johnson continues policy, and we generate a new neighbor of that. So substitute Johnson with Arsenal. Arsenal is a football team, so this is closer to being about sports. If we do that again, well, we still haven't passed the threshold of 95% here, but we're quite close. So I'm going to try substituting policy with winning again. And then it says, OK, there's a 97% chance this is about sports, so a very high probability And that's it. We're done. We're going to output this sentence. Let's see. Is there anything else to say here? No. OK. So that's all I had. Thanks for listening. And I guess James and I will take questions now.